So today I'm going to tell you about confidence intervals and how to interpret them. And confidence intervals are pretty fundamental idea because they help us um, report on how accurate our estimates are, how much error might be in them. Yeah, Wednesday I told you a little bit about estimation, the variability of the estimate, and using the Bootstrap method to estimate the variability in our estimate. And today I'm going to show you confidence intervals. And then Monday we'll start switching topics and we'll talk about methods for describing a distribution. Okay, sometimes called descriptive statistics. So the Bootstrap. I realized talking to a couple of folks after lecture last time that maybe this was a little confusing. So I wanted to try one more time. If you got it, great. If you didn't get it, give me another chance, would you? I want to tell you a story that's half true, the half made up. So my brother wanted to be a sailboat designer when he was a kid. He really, really wanted to do it. So he managed to get an internship just before college, working for someone who designed boats, and they had well, not a wind tunnel, but what do you call it? Like a water, a water thing where you could put a model in it, and they would test how the water propagated through. And so he was an intern, and so he got assigned kind of the crummy jobs. And one of the jobs, one day his boss came and said, "Hey, we're gonna test this sailboat, and we found someone who has one at this marina 3 hours away. And so I want you to drive there and get measurements for everything so we can make a scale model." And so my brother's like, okay. So he takes off, he drives 3 hours there. He takes measurements. It's this far from front to back, this far to the side, all the different dimensions. And then he drives 3 hours back, and he comes back the next day to his boss and says, "Okay, boss, I got the measurements. It's 19 feet long and it's 4 feet wide," and so on. He's rattling off these numbers. The boss said, "That's great. And okay, and what was the variation in your measurements? How much is the error?" And he's like, "Variation?" He's like, "Boss, like, oh yeah, don't you know we take all measurements 5 times so we can check and see how accurate your measurements might be. You do it once from front to back, once from back to front. Do it, and then we look at the range of those numbers, and that tells us how accurate it is. We really need to know that for the scale model." And my brother was like, "Oh." Boss like, "Okay, tomorrow you got to drive back out there and do it all over again." Brother's really disappointed. Goes to bed. It's like, "Oh man, I got to do the whole thing again." And then the next morning he wakes up, has a shower, and has a brilliant idea. And let's see if you can predict what the brilliant idea is going to be. He doesn't want to drive all the way out there. So instead, what he does is he decides to go out in the backyard in the dirt. And he takes all his measurements and he draws the sailboat in the dirt in his backyard. Makes a mock sailboat, a replica of it. This one's 19 feet long and 4 feet wide, and so on. And then he gets out his measuring tape and he measures 5 times the length of this and 5 times the width of this. And now he knows how much variability there is in his measurement, giving him a sense of how much you're off by. All right. So it's a halfway made up story. But I hope it gives you some idea of the Bootstrap. This would be a reasonable procedure to find out how much is like the variability in my measurement. If I measure something 5 times, I'm not going to get the same thing exactly every time because I'm not perfect in reading off the numbers or setting everything up. But it'd be a reasonable way to find out when I'm measuring something that's 19 feet long about how much error is there in my measurement. And we can do that measurement on the replica rather than on the real thing, and it'll still be just as valid because the measurement error probably depends on, like how long we're measuring, and maybe it doesn't have to be the exact boat. Okay. Yeah, so this is not measuring systematic error, but it's measuring kind of like random error from I don't know, you didn't line it up exactly right. It's not, it's something that's a little bit different every time. Okay, so don't take this analogy too seriously, but that's basically the idea of the Bootstrap. So in the Bootstrap, we're dealing not with measurement error because of my imperfection and able to lay out the measuring tape exactly on the right dot, but the error now is due to sampling error, due to to the randomness in the choice of the sample that affects the particular outcome. So in the Bootstrap, you know, in the ideal world, you take the population. Well, okay, so we have the population. That's all the data, and then we take a sample from that, and we're getting some estimate from the sample, and we'd like to know how much error there might be in that estimate. How much variability might there be? So you can kind of think as the population is like the real sailboat, and the sample is like our replica that we drew in the backyard. And then the gold truth way, if we're willing to drive 3 hours, if we're willing to spend a lot of money on getting new samples, the ideal way would be to take the population, and we could draw a bunch of additional samples from the population. And we could get the estimate for each and see how much variability there is in that estimate. And that would tell me how much randomness is affecting my estimate. In other words, how much error there usually is in my estimate. But I don't want to drive 3 hours. I don't want to pay for the cost of more samples. So instead, the Bootstrap says what you can instead do is draw a bunch of samples from your sample, draw resamples, okay? And look at what the variability is when you're drawing from the sample. And the idea of the Bootstrap is, as long as your original sample is not too small, then its distribution is probably pretty similar to that of the population. Or in other words, the mock replica boat is probably pretty similar to the real boat. And so the variability that I get from drawing resamples from the sample is probably about the same as the variability I get from drawing samples from the population. Okay, that's the idea of the Bootstrap. Let me check in and see how we're doing. Maybe we'll do a little class poll. How about we do a poll where you go into participants and you say, click for me, yes, if you're thinking it all makes sense. No, if you're thinking I'm pretty confused, and coffee cup if you're like, I don't know, I'm a little fuzzy. I kind of get it, but I kind of don't. Okay. Thank you. Thank you for the feedback. So what I'm getting out of this is it's not solid yet. For some of you, it's making sense. For some, it's a little iffy. So let me suggest maybe reading the chapter in the textbook. And we should have some practice questions for you as well. And hopefully between that, maybe that'll solidify. Yeah, how could my brother resample? I mean, it's just an analogy, but the idea is you lay out your measuring tape and you measure, and then you try and do it again. And if you've ever had to measure anything long and you try to do that, you might find the first time you get 19 foot and 3/16. And the next time it's like, oh, it looks a little closer to 19 and 4/16. Just because, you know, we're not perfectly precise in how we lay out things. So it happens. The resamples are the same size as the sample. Yeah, that's very important because the amount of variability probably depends on the sample size. So it's very important that you use the same sample size in your resamples as you would with your sample when you're estimating. Yeah, so bootstrapping is just drawing samples and resamples to help you get a measurement of the error, the typical error that estimates will often have. If you resample from the samples, isn't that the same as sampling from the original? That's the idea, is that it's pretty similar. Yeah, so that's why, you know, if you could sample from the original, you would, and you would look at the variability in the samples from the original, but we can't afford to. So we instead do these resamples, and they're pretty similar. The variability in them is pretty similar to the variability in sampling from the real thing. Wouldn't we always want to bootstrap? Yeah, totally. Always. Absolutely. It's really useful. Anytime you're making an estimate, probably you want to know not just what the estimate is, but how accurate your estimate is. How much might the randomness have affected your estimate? And so the bootstrap is often really useful. Yeah. Yeah. So how the resampling in the boat was just measuring the drawing over and over again. Yeah. It's an analogy. Don't take it too seriously. But I wanted to give you something to try to understand what's going on. What are the limitations of the bootstrap? We'll get to that in a moment. How do you resample data? Like, how do you get different data if it's the same sample? Yeah. This might look weird that I'm drawing, I have a sample of 300 and I sample 300 from it. Won't that be exactly the original sample? No, it won't be. You see, if I if I did without replacement, then it would be exactly the same as the original sample. But I'm doing with replacement for the Bootstrap. So out of these 300, I pick one and I add that to the resample. And then I put it back. And so now I pick again out of the 300, pick one. And it could be a small chance, but it could happen that that's the same one I picked the first time. So this resample will have some items that are duplicated and some items in the original sample that don't appear at all. And each resample will typically be different. Okay. That's the Bootstrap. And then here's how we're going to use the Bootstrap. We're going to use the Bootstrap to create something called confidence intervals. And a confidence interval is, in addition, is a way you can supplement your estimate with some measure of how accurate your estimate is. Okay, so a confidence interval, it's an interval. An estimate is a single number like 19 feet. And a confidence interval is an interval. It's a range. It'd be like 18.9 to 19.1. That's an interval. And it's an interval of estimates. It'd be like saying, you know, all of those values are plausible values for the parameter. I don't know whether it's exactly 19, but I think there's a good chance it's within the 18.9 to 19.1 range, roughly speaking. Okay, that's what a confidence interval is. The reason we end up with an interval, the reason we end up with some uncertainty is because of the random sampling. The sample, there's some randomness in how we chose the sample. The sample could have turned out differently. And so if you were to do the sampling, you'll get an estimate that's not exactly equal to the parameter. It might be a little high, a little low. And so the confidence interval is measuring how much high or low it might be. The 95% number is called the confidence level. So let me talk to you a little bit about what I mean by confidence. See, this interval intervals, these can be good or they can be bad. An interval is good is if the true value of the population parameter is indeed within that range, within that interval. But it's bad, it'd be bad if the population parameter fell outside of it. So the interval is trying to say, I think there's, it's likely the population parameter is in this range. Maybe I don't know what the exact value is, but it's pretty likely it's within this range. And that 95% is an attempt to measure how likely it is, basically. But we got to be a little bit careful what I mean by that. So I'm using a little bit sloppy wording. So I'm going to try to be a little bit more precise now. This confidence level could be any percentage between 0 and 100%. And a higher level of confidence means it's more certain that my interval will be good. In other words, that the true population parameter will be somewhere in the interval. But to get higher confidence, I need a wider range. Okay. And the confidence, we have a process that given a random sample will give me not just an estimate, but a confidence interval. And the confidence is in that process. So I want to be a little careful about what we mean by 95% confident. What 95% confident means is that this process, if we were to use it over and over again across our lifetime, would generate a good interval about 95% of the time. Okay? It doesn't mean that there's a 95% chance that the population parameter is within this interval. Because once you have an interval, the population parameter either is or isn't in that range. There's some truth about it. We just don't know. It's not known to us, but the interval is either good or it's bad. We just don't know which it is. So instead, what this confidence refers to is sort of like an aggregate. If you were to get lots of measurements or do lots of polls or repeat this process many times over your career, then 95% of those you would have generated a good one, and 5% you would have generated a bad one. You won't know which ones are good and which ones are bad. So this is sort of only an aggregate that most of the time you'll be right. This is the kind of the promise that you get, the confidence you get is most of the time you're right, but some of the time you'll be wrong. And that's unavoidable. It's unavoidable that there is some uncertainty and that some of the time you'll be wrong. Okay, so let me say again what I mean by a good interval. Let's suppose that the confidence interval that I get out is an interval, a range from 18.9 to 19.1. All right. That interval is good if the parameter I'm trying to estimate is in that range. Like if the parameter was 19, that'd be a good interval. If the parameter is 19.01, that'd be a good interval. But if the parameter's outside that interval, then it's bad. Like the parameter was 19 and a half, not within that interval, that would be a bad interval. Now, we won't know whether the interval was good or bad for any particular interval we generate because we won't know the population parameter. But that's what I mean by good versus bad. Okay, so the confidence here refers to the confidence that the thing we're trying to estimate is somewhere within this range given by the confidence interval. Talk about the direction of the alternative. We're not doing hypothesis testing right now. We're just trying to get an estimate. Like, for instance, maybe we did a poll of how people are going to vote in the November election. So we did a poll by calling up a random sample of people and counting how many of them said they're going to vote for Biden. Okay. And then from that, we're trying to estimate how many will vote for Biden in November. Now, we only polled maybe 300 people, let's say. So there will be some error in our estimate. There could easily be some error in our estimate because of the random sampling there. We might have just happened to end up with our random sampling having slightly more Biden supporters or slightly fewer Biden supporters. So there's some error. So the confidence interval is a way to measure that error. Confidence interval, you might find a poll report margin of error. So it might say maybe we predict that 50% of people are going to vote for Biden with a 4% margin of error. So they're basically saying a confidence interval is 46% to 54% are going to vote for Biden. Okay, so there's no hypothesis testing right now. We're just trying to estimate what fraction of people in the entire population are going to vote for Biden. Okay, so let me just work through some code so you can see it in action. So remember last lecture we were working with these San Francisco salaries of San Francisco employees. In this case, we happen to have all the data, so we can have our God's eye view, but I'm going to imagine that we don't. I'm going to imagine you're a data scientist, a union rep, someone like that who only has a sample of the salaries for 300 of the employees. And let's say we want to estimate the median of the population. So the median, the estimate you would get from the sample is 117,000 in this case, which was a little high compared to the actual true number. We can tell because we have the God's eye view, but the data scientist wouldn't know. So we're going to use the Bootstrap to figure out how much variability there is in these estimates as a result of sampling just 300 people out of all employees. And the way we do it is with this code here that resamples from our sample. Okay, generates a resample from our sample of 300 and then finds the median of that resample. That's what to do if we want a single resample. And then we're going to do this many times. We're going to do, let's say, 1,000 of these. Okay, so we're going to generate 1,000 resamples. Like this. So that generates a resample and generates a median, an estimate from that resample. And then we're going to save them all in an array. We're going to do the standard way we do that. Start with an empty array in each iteration of the loop. We append to this array that we're building up. And it would help if I could type. Okay, so that's going to do 1,000 resamples. And then what I'm going to do next is I'm going to plot all of these, plot the histogram of these estimates, the medians from these resamples. And there's what the histogram looks like. Okay, so the blue dot here is the estimate we got from our one sample, and then we resampled and we looked at what the estimates from the resamples were, and we can see how much variability there is here. Typically about, I don't know, maybe it goes up plus or minus $8,000 in the estimate often. Sometimes it's more than that. Occasionally it's more than that, but that's kind of the most commonly, plus or minus 5,000, plus or minus 8,000. So that gives me an idea of how much error I should expect would often occur if I estimate my population parameter using a sample of size 300. So now let's get a confidence interval. Yeah, I was totally just eyeballing it here. That was totally subjective eyeballing it. So now let's make it more systematic. And a confidence interval is a way to make that more systematic, to make it more quantitative. What was the red dot? The red dot is using our global God's eye view of knowledge of all of the employees for the entire population. The population median is 100 and, I don't know, 13,000. So our estimate was a little high in this case. All right, so let's get a confidence interval. The way we're going to get a confidence interval is we're gonna look for a range of values that would cover these resampled estimates 95% of the time. Okay, so we're going to generate an interval of values here so that there's only 5% of the distribution falls outside that interval, and 95% of this distribution falls within it. So how do we do that? If we want 5% to fall outside of it, that means we want 2.5% on the left-hand side and 2.5% on the right-hand side to be outside it, and the middle 95% to be in it. So we need to figure out how to draw an interval. So if I drew an interval like right here, that would be too narrow. That would only cover, you know, a couple percent of the distribution. If I drew an interval like right here, that might cover maybe 50% of the distribution. Still too narrow. If I drew an interval like all the way across, it's too wide. That covers 100% of the distribution. So I'm going to draw an interval from somewhere around here to somewhere around here. And how do I calculate that exactly? The way I calculate that is I wanted 2.5% to be the left of it. So the left end of my interval should be the 2.5 percentile of the data. And I want 2.5% to the right of it. So my right end of the interval should be the 97.5 percentile, 100 minus 2.5. All right, so I compute the endpoints of the interval, and then now I can do the same plot with the interval from that left endpoint to that right endpoint shown in yellow. And the yellow here is the interval we got in this way, the interval that covers 95% of this distribution, and that's the confidence interval for our estimate. So our estimate is, looks like the estimate is about $117,000, and the confidence interval is from about 109,000 to about 123,000. So what you might report is from your sample is say, I have a 95% confidence that the population parameter is in the range 109,000 to 123,000. And that now lets the recipient to that information tell how much uncertainty, how much error, how much you've narrowed down what the true value is likely to be. Okay, is it always 95%? No, 95% is a typical value for the confidence that you might want to have. But you could ask for a 99% confidence interval if you don't like to be wrong. 95% is a common thing you'll see reported. It's kind of a convention, an arbitrary convention. And for those of you who are noticing, that's really interesting that 95% is kind of like 100% minus 5%. And you're remembering 5% is a conventional value for a p-value cutoff. You're right. These are super closely connected. And I'll talk about the connection in a moment. But you're utterly right. It's just like with a hypothesis test, we only want to make the mistake of rejecting the null hypothesis wrongly 5% of the time, let's say. Same thing here. We only want to make the mistake of having the true value be outside our confidence interval 5% of the time, say. Okay. Why would I not go with the values that appear 100% of the time? If I want a 100% confidence interval, the answer is it would be really, really wide. And then it would give me very little information. Okay. Still confused about why I wouldn't choose 100%. Here's the thing. There's a tiny, tiny chance that you get a humongous error in your survey. Let's say we're doing a random sample of 300 people from the US population to find how many are going to vote for Biden. There is a chance, it's incredibly unlikely, but there is a chance that just by random luck, you happen to pick a sample where all 300 of them are Biden voters. And then you get out of that sample, 300 of them are, and you report in the newspaper, 100% of people are going to vote for Biden. And you were way, 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 way wrong. It's a chance. It's a tiny, tiny infinitesimal chance. There's also a tiny, tiny infinitesimal chance that your sample contains no one who's a Biden supporter and that your estimate is 0%. So if you want, what is that telling you? That's telling you that you can't really put any reasonable limits on how large the error could be if you want to have no chance of error, because there's a tiny chance your estimate is wildly off. So if you wanted 100% confidence, your interval would say, well, there's between 0 to 100% of people are going to vote for Biden. That's even if you got a completely normal sample. You'd always be reporting a confidence interval that said between 0 to 100% of people are going to vote for Biden. Well, gee, thanks. I kind of knew that before you got the data, so not very useful. So while we would love to have certainty whenever we're dealing with randomness or with sampling or with data, we rarely have certainty, and we have to just get comfortable with the fact that sometimes we're going to be wrong and there's going to be some uncertainty. Okay, I'm following all your comments here, your questions. Yeah, if I instead of wanted a 95% confidence interval, if I wanted a 99% confidence interval, would that interval be wider or be narrower? It'd be wider because it needs to cover more of the distribution, so it needs to be wider. So if you wanted a 99% confidence interval, in some sense, it'd be less informative. It wouldn't narrow down the range of values as much. Narrower is better in a sense that a narrower interval gives you more information. It helps you narrow down what the true value is to a smaller range. So it means that your estimate was more precise or more accurate. So yeah, narrower is kind of better. All right. So we did this whole process with one sample, and we got an estimate and we got a confidence interval. Now, in this case, was this confidence interval good or bad? The red dot is where the true population parameter is. We know all the data, so we can tell whether this estimate was good or bad. Was it a good or a bad interval? Good. Good, because the red dot was within this yellow range. Now, another data scientist who got a different sample, if you'd gotten a different sample, this would have turned out differently. So we can try and see what would have happened if we had gotten a different sample. And I'll just rerun all the code and we'll see what the data scientist would have gotten if the sample was different. So now it's a different distribution, a different estimate, and a different confidence interval. This confidence interval was also good. Okay. So you could imagine doing this many, many times. You could imagine saying, let's imagine repeating this experiment many times. Just hypothetically, we're going to simulate it. We're going to imagine 100 parallel universes where there's 100 different samples, and each data scientist in each universe is getting an estimate, and they're getting a confidence interval. And so I did this, ran the code to do that, to simulate that setting. The red line here represents the true population parameter, the true median of all San Francisco employees. And each yellow line is a different confidence interval in a different universe. So there's 100 universes, and the universes are kind of stacked up vertically. And you can see how in each universe, the data scientist gets a little bit different confidence interval. Some of the confidence intervals are fairly low, some are fairly high. Many of the confidence intervals are good. The true value, the red line, is contained within the interval. But there are a few that are bad, like there's one right here in the middle that's bad. The population parameter is a little bit lower than the interval. It's outside the interval. So that was a bad one. And this, let's see if we can tell how many were bad. Here's a bad one, that's 1. I can't tell if that's bad or not. Let's say it's not. Here's a bad one, that's 2. There's a bad one, that's 3. There's a bad one, that's 4. So it looks like 4 bad ones. And that's about what you'd expect after about 100 trials. What the 95% confidence means is that after 100 trials, you'd expect to get about 5 bad ones and about 95 good ones. Not necessarily exactly, but the more trials you do, the more these times you do this process in your lifetime, the closer the proportion of good ones will be to 95%. Okay, so 95% of the time when we reported this to a client, we were right that the value truly was within that range, and the 5% of the time, whoops, it wasn't. Okay, so that's a confidence interval. That's what confidence means. So I want to check your understanding. Oh, I want to give you a caveat first, actually. Someone asked, how do I want to do this? All right, I want to do it like this. I want to do a test. I want to check and see where you're at. Let's suppose that we have a population of mothers, and we want to know the average age of the mothers, and we compute a 95% confidence interval using this procedure I just described with the Bootstrap, based on some sample. And the confidence interval we get is the range 26.9 to 27.6 years. Okay, so that's the confidence interval you got from this process. Now my question for you is true or false? About 95% of the mothers in the population are between 26.9 to 27.6 years old. All right. Everyone who says false, no verdad. Right on. Right. This is false. This is false. And the reason is we're trying to estimate the average age of the mothers. There's probably the age of the mothers probably spans a whole range from maybe 20 to 40 or something like that. It's unlikely that 95% of them are in this very narrow band. Instead, we're referring to the confidence interval refers to the average of the ages of all the mothers in the population. So this is not the correct interpretation of a confidence interval. Confidence interval is talking about the average of the population. It's talking about the parameter. All right, so you got to be careful about what the confidence interval is telling you about. It's not telling you about a bar, a bin in the histogram of ages of the mothers. It's telling you about the average of that distribution of that histogram. Let's do another one. We did the same experiment. Took a random sample of mothers. We used that to estimate the average age. And I just want to highlight, I was talking before about medians. Now we're going to do this for averages. You can do the same process for any parameter of the population. So the one we're looking at now is average. So we got a confidence interval as before for the average age of the mothers in the population. That confidence interval as before is 26.9 to 27.6. So same as before, but now I'm going to ask you a different true or false question. True or false? There's a 0.95 probability that the average age of mothers in the population is in that range. All right, I see lots and lots of trues. True that. Handful of falses. Falses is starting to gain. All right. Someone type it for me in chat a reason why someone would reasonably say true. Tell me what the thought process might be behind true. Give me an argument for true. It looks believable. We're talking about 95% confidence. That sounds like a 95.95 probability. Crickets for true. I'm changing my answer. Okay, give me some reasons for false. We're gonna try to figure it out amongst ourselves. So someone type in the chat some reasons why you think false. Give me an argument for false. False because we're 95% confident. That's not the same as probability. Okay. At this point, I don't even know. I'm with you. I'm super sympathetic. All right. I'm asking these questions because I know this stuff always trips up people every year. So it's completely understand if this is a little confusing. I chose it because it's confusing. All right. The average age of mothers is a number that's constant and not random. Oh, ding, 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 ding. All right. $64,000 prize right there. The population is what it is. There's nothing random about the population. So there's some set of mothers. They each have some ages that has some average. There is some true value for the average age of the mothers. We might be ignorant about what it is, but there still is an answer out there. God can see what that value is, even though we don't know it. So there's no randomness in that. The only randomness is in who is chosen to be in the sample. Okay, so now when you have this range, 26.9 to 27.6, the true average either is in that range or it isn't. We're unaware of whether it is or isn't. We don't know, but it's either true or it's false. And God knows. We don't know. Okay, so it's not right to say there's a 95% probability that the average is in that range, because there's no probability involved. There's no randomness. It's just a statement that's either true or it's false, and we're unaware of. So I realize it is common to use probability to talk about our ignorance, to try to put some measure on what we think is the likelihood that it's true or it's false, given our limited information. But it's not actually technically correct in this case, because the statement is either true or it's false. So it's not right to use probability here. So instead, what's going on is that we have what's we say 95% confidence to try to draw this distinction that it might be or it might not be. And if you were to do this process 100 times, about 95 of them, it would have been true, and about 5, it would have been false. And you still wouldn't know which were which. Okay. So there's no chance involved in that, in whether that interval is a good one or a bad one. All right. I don't know if that makes sense or not. I realize this is pretty tricky. This is kind of nitpicky, pedantic stuff. So if you understood everything about confidence intervals, but you didn't understand that one, okay, you're doing pretty good. But I do like, I'd love it if you could also get this subtle point as well, which is it's not the probability that the population parameter is in the range. Yeah, 95% confidence interval means that 95% of the intervals you generate this way will have the average age in them, which might not sound very reassuring because we only generated one interval. So this reassurance is only a very long-term reassurance. That reassurance doesn't, I don't know how much reassurance it gives you about this one interval. It kind of gives you a reassurance over your lifetime that, you know, you'll be right some and you'll be wrong some, but you'll be right a whole lot more than you'll be wrong. So no, you can't say there's a 95% probability that this interval contains the average. Yeah, you could say that we have 95% confidence with this associated with this interval. You could say the 95% confidence interval for the average age of the mothers is 26.9 to 27.6. you could say we have 95% confidence in this interval. Okay. All right, so that's confidence intervals. You can use the Bootstrap to calculate confidence intervals for you. The slogan that I want you to remember is estimates are not a single number. They're a range, because there's some uncertainty, there's some imprecision in our estimates due to sampling. So when you are reporting results to others, instead of reporting a single number can be misleading. It implies that you know what the answer is and that you have a great precision. And it's often more helpful to report a range to reflect the uncertainty we have. Okay, so you can use the Bootstrap for this. The Bootstrap is something you can use for any population parameter, almost any population parameter. It's not limited to just the median, not limited to just the mean. In fact, one of the things that's really exciting about this course for me is this isn't how I learned how to compute confidence intervals. I was taught a formula, if the distribution is normal, and if you're doing the mean, and you can use this formula. And if you want the median, oh, whoops, we don't have a formula. Sorry, you're out of luck. Or if the distribution isn't normal, oh, whoops, sorry, we don't have a formula for you. So this is I like this way of teaching this stuff much better, because it hopefully helps you understand what the meaning is, and also can be generally applicable to basically any distribution and any parameter you want to estimate. Now, basically any. There are some rare cases when you should not use the Bootstrap. If you're trying to estimate a parameter that's a very high or a very low percentile, like you want the min salary in the population or the max salary in the population, the Bootstrap turns out is not a good measure. And you might not get very good estimates either from your sample, because that's influenced by a single element in the population, and the chances that your sample happens to contain that single element is pretty low. So in general, if you're trying to estimate any parameter that's affected by rare elements of the population, then the Bootstrap might not be an accurate way to measure error due to sampling. Also, if the probability distribution of of the population, of the statistic, is really weird looking. So if you do this resampling and you look at that distribution and it's kind of bell curved-ish, you're fine. But if it looks really weird, it's like some something, then you're on shaky waters and something might be wrong, and maybe the Bootstrap's not appropriate. Or if your original sample is very small, you got a sample of just 5 elements or something like that, then the Bootstrap's on shaky ground. But most of the time, the Bootstrap's going to be just fine. Okay, now, some of you were pointing out something before that I thought was really interesting, which is you were highlighting sounded like there might be this connection between 5% cutoff for a p-value in hypothesis testing and 95% confidence interval. And you were spot on. You have really good noses if you were noticing that smelled kind of similar. There's super close connection between the two of them. You can use confidence intervals for hypothesis testing. Okay, so suppose that I have a null hypothesis that looks something like this. My null hypothesis is that the population average is 27. And my alternative hypothesis is the population average is not 27. Okay, so suppose I want to do a hypothesis test of that. And I have a cutoff, maybe it's a 5% cutoff. Well, then you can use a confidence interval to do this hypothesis test. So what you can do is you can calculate a 95% confidence interval for the population average using the methods we just showed you, and then check whether 27 is in that interval. And if it's not, if it falls outside the interval, then we reject the null hypothesis that 27 is the population average. Okay. If 27 is in the interval, then the null remains plausible. You can't reject the null. Okay, so a confidence interval gives you a way to do a hypothesis test when your hypothesis test is a statement about the population average. And in fact, here's something really neat. If you have a 95% confidence interval for the population average, that is the range of values that would be accepted, that if you took one of those values and stuck it in your null hypothesis, then you would not reject the null. Okay, so let's say what I'm measuring is how long I live after I take this drug. And my confidence interval for that is 3 to 7 years. Then one interpretation of that, a 95% confidence interval of 3 to 7 years, is that if I took a null hypothesis stating that the average is 3 years, that would not be rejected by a hypothesis test. If I took a null hypothesis stating the average is 4 years, that would not be rejected. If I took a null hypothesis saying the average is 5 years, that would not be rejected. 6, 7 years, those null hypotheses would not be rejected. But a null hypothesis stating that the average is 8, the population average is 8, would be rejected, or 2 would be rejected. So the confidence interval has a very close connection to hypothesis testing. The confidence interval gives you a range of values for the population average that if you tried to do a hypothesis test with one of those values as your null, the null would not be rejected. And anything outside the confidence interval is a candidate value. If you stuck it in the null hypothesis would be rejected. So you could think of the confidence interval as kind of like a range of values for the population average that are plausible. Okay. And the connection between the cutoff and the confidence level is 95% confidence corresponds to 5% cutoff. 99% confidence corresponds to a 1% cutoff, and so on. Okay, so just as in a null hypothesis test, there is a small chance that you wrongly reject the null, even though the null was actually right. There is a small chance that you construct a confidence interval where it's wrong, it's bad. The parameter is actually outside the confidence interval. And that chance is the p-value cutoff, or 100 minus the confidence level. Okay, so that I'm going to stop here, and next week we're going to start looking at descriptive statistics, ways to describe a distribution. Thank you, and I hope you have a great weekend.